All right, so we are moving forward from integral calculus and moving on to sequences and series. At this point, most of our studies will concentrate on the convergence or divergence of sequences. Now, remember that a sequence is a function whose domain is the set of positive integers, where the terms of the sequence are given by a sub 1, a sub 2, a sub 3, and so forth. The nth term is given by a sub n, and the entire sequence is denoted by the squiggly brackets and a sub n. A sequence will converge to a limiting value if the limit of the nth term as n approaches infinity is equal to L. If no value exists, then the sequence diverges. As a consequence of this, we can define a function as that behaves similarly to the sequence, whereas the function is going to be continuous. And then primarily we can treat the limits of sequences much like we do the limits of functions. So let's go through a little bit of brief review of sequences. So we have an explicit formula given below, and by explicit that means given an n, I can tell you what that term will be. And then we're going to define it recursively, which means the term will depend upon the previous term. So we have a sub 1 is going to be 2 to the first, so that's 2. A sub 2 is 2 squared, so that's 4. A3 will be 8. A4 will be 16. And A5 will be 32. So that gives me my recursively defined sequence. Each successive term I have to multiply by 2, so it's 2 times a n minus 1. That's that. Okay, so looking at b, we have b sub 1 is going to be 3 to the first over 1 factorial, so 3 over 1 factorial, which gives me 3. b sub 2 is going to be 3 squared, so 9 over 2 factorial, which gives me 9 over 2. b3 is going to be 3 cubed, so 27 over 3 factorial, which is 27 over 6, so that's 9 over 2. b4 is going to be 3 to the 4th, so 81 over 4 factorial is 81 over 24, which simplifies to 27 over 8. b5 is going to be 243, 3 to the 5th, over 5 factorial. So 243 over 120, which simplifies to 81 over 40. Now, our recursively defined sequence, I can see that I'm going to multiply each term by 3 over n, and then be the n minus 1. Now, for example 2, I'd like you to work on those on your own, and we'll talk about those in class tomorrow. Substitute values of n and see if you can plot those points and figure out which sequence matches which graph. So moving on, we're going to go on to example 3, and we're going to define each sequence below. So there's more than one correct answer for each. Now, as you work through these, don't try to take the whole thing at one point. Look at each individual part. It'll make it much easier. So I can see in this first one that my numerator is changing by n. And then my denominator changes by n plus 1 times n plus 2. Now this next one you should recognize as an arithmetic sequence. And I see that my common difference is 3. So using the formula that I remember from Algebra 2, I have a sub n is equal to my initial term plus my change times n minus 1. Simplifying, we have negative 1 plus 3n. Now this last one is a geometric sequence. And using my formula, I know that's a sub n is equal to my initial value times my r. I'm going to go back here and I'm going to say r is equal to negative 1/2. And then that goes to the n minus 1. Okay, so in many problems, we're going to be asked to manipulate and simplify factorials. So we're going to go ahead and practice some of these. Now we know that since we have an n minus 2, and I'm only going to do one, and then I'm going to have you do the other two. We'll talk about those in class tomorrow. So I have an n minus 2, so I'm going to leave that in the denominator. Now I know that n factorial is going to be n times n minus 1 times n minus 2 times n minus 3 and so on. But I can write n minus 2 factorial, which means then that this simplifies to n times n minus 1. Now I want you to continue through those and we will go over those answers in class tomorrow. Okay, oops, let me go back a page. So you should recognize these behaviors as the same limit rules that we have from functions. Okay, so we can add, subtract, multiply, and divide limits of sequences intuitively, which also means then that L'Hopital's rule is going to apply, as well as the Squeeze theorem. So remember from the Squeeze theorem when we talked about limits, if the limit as n approaches infinity of a sub n is equal to L, and the limit as n approaches infinity as of b sub n is also equal to L, and there exists an integer such that the function a sub n is between, or c sub n is between a sub n and b sub n, then our limit as n approaches infinity of c sub n equals L. So what we're doing is we have this sequence. I'm going to try to sketch it here. So if we have a sequence, and we know that this is our a sub n, and then we have our b sub n, if we know that we have a sequence that, goes all over the place, but it stays between a sub n and b sub n, then I'm going to write this as a sub n. It doesn't really matter which order we do this in. I'm going to say maybe a sub n is less than or equal to c sub n is less than or equal to b sub n, then we know that the limit as n approaches infinity of c sub n equals L. Okay, so let's talk about what that means. Okay, so we want to show that this sequence converges and find its limit. So we have that c sub n, it's an alternating sequence. So we have negative 1 to the n over 1 over n factorial. So we need to find a sequence that behaves similarly, or at least that we can define. So if you flip back to the front page, the factorial function will grow faster than any exponential function. Okay, so that gives us some information. So let's define an a sub n. And we're going to define that is negative 1 over 2 to the n. Now, I will explain in class graphically tomorrow why I chose that one. Now, I know that the limit as n approaches infinity of negative 1 over 2 to the n is equal to 0. So then we need a b sub n. So b sub n, we're going to have as the positive 1 over 2 to the nth, and the limit as n approaches infinity of that one is also 0. Now, let's talk about why we know that we can do this. And I'll show this graphically in class tomorrow. So we're going to compare n factorial with 2 to the nth. Myself a little more space here. Okay, so let's talk about what n factorial looks like. N factorial is 1 times 2 times 3 times 4 times 5 times 6 times n. Okay, so we can simplify that to 24 times 5 times 6 times dot 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 times n for n greater than 4. All right, so let's look at 2 to the nth. 2 to the nth is going to be 2 times 2 times 2 times 2 times 2 dot 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 times 2. So that is going to be 16 times 2 times 2 times dot 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 times 2 for n greater than 4. Okay, so with that, I know that for n greater than 4, n factorial is going to be greater than 2 to the nth. Okay, so then we know that negative 1 over 2 to the nth is going to be less than or equal to negative 1 to the nth less than or equal to 1 over 2 to the nth. Okay, so we know that our limits the limit as n approaches infinity of negative 1 over 2 to the nth can be less than or equal to my limit as n approaches infinity of negative 1 to the nth over 1 over n factorial can be less than or equal to my limit as n approaches infinity of 1 over 2 to the nth. Well, I have those limits, so I know that 0 is less than or equal to my limit as n approaches infinity, negative 1 to the nth over 1 over n factorial is less than or equal to 0. Therefore, by the Squeeze theorem, the limit as n approaches infinity of negative 1 to the nth, 1 over n factorial is equal to 0. Okay, so let's keep going through this. We're going to do a couple of them, and then I want you to finish these, and we'll talk about them in class. So, sometimes the terms of the sequence are generated by a rule that's not explicitly stated. So we need to start recognizing formulas, but also determine that to help us determine whether that sequence converges or diverges. So, if we have the sequence that starts a sub n is 1/2, 1/4, 1/8, we could write that as 1 over 2 to the n. And that one we can see, we know that that's going to converge to 0. Okay, Well, b sub n is the same form, gives us the same first three terms, but it gives us a different fourth term. We can see that that one converges to 0. So I want you to do c sub n and d sub n and determine what those sequences converge or diverge. So you have to have an explicit formula to be able to solve and determine the sequence, the convergence or divergence. So we're going to start with, I'm going to get you a explicit formula for a sub n, and then have you go ahead and figure out whether or not this sequence converges or diverges. So again, work with the numerator and the denominator separately. So I can see that a sub n, this in the brackets, so I have the even numbers. So even numbers are going to be 2 times n. 2 times n. Sorry, that should be 2 to the n. That was a typo, sorry. 2 to the n. Odd numbers, these aren't even. All right, let me back up. These are not even numbers. These are exponents of 2. So I can see that these are powers of 2. So that should be 2 to the n. The bottom is our odd numbers. So that gives us 2 to the n minus 1. If we need even numbers, so this is just a note, even numbers will always be 2n. Odd numbers, 2n minus 1. So you want to find the limit as n approaches infinity of 2 to the nth over 2n minus 1. So we are going to stop there, and we are going to finish with monotonic and bounded sequences in class, and then do some practice in class on those.